My name is David Godwin, and I'm the coordinator for the Southern Fire Exchange. Today we're excited to have our guest speaker, Dr. Scott Goodrick, research meteorologist with the U.S. Forest Service. Today, Dr. Goodrick will be giving a presentation on the impacts of El Nino and La Nina events on the 1998 Florida wildfire season, and will also include some discussion of our upcoming season. Scott Goodrick, our guest today, leads the Center for Forest Disturbance Science at the U.S. Forest Service Southern Research Station. He's located in Athens, Georgia, and he's been a research meteorologist for the Forest Service for over 13 years. His primary research areas are related to fire and atmosphere interactions and smoke management. Prior to joining the U.S. Forest Service, he was the fire weather meteorologist for the Florida Division of Forestry, now called the Florida Forest Service. So welcome, Scott. Welcome, Dr. Goodrick. We're excited to have you here today. We have a good turnout, and I'm really looking forward to your presentation. So just 1 second as we switch over things.
All right. Thank you very much. All right. So the topic today is taking a look back at the 1998 Florida wildfires and what, if anything, El Nino and La Nina had to do with them, which you'll agree at the end was quite a bit. So kind of an overview of what we're going to go over today is we're going to look back at some of the conditions for the 1998 Florida wildfire season, a little bit on what happened, and then look at the connection between the El Nino Southern Oscillation, or ENSO, and the Florida wildfire events, and then finish up by looking at trying to see if there's any parallels between what happened back in 1998 and what we see happening right now in 2016. So before we start talking about what happened in 98, this is kind of just to orient you on a view of kind of average Florida fire season. The top graph kind of shows the number of fires by month on average. And you can see that the number of fires peaked there in the early part of the year and then dwindle off as we head into the summer months and then begin to pick up again in the fall. Florida has kind of an interesting climate in that you have 2 seasons for much of the state, a dry and a wet season, with the summer months being the wet season and the winter months tending to be drier. And as you move up towards the northern part of the state, you get into a regime where you still have that summer wet season, but you also begin to pick up a few more frontal passages during the winter and spring months to give you a secondary peak in rainfall. The lower graph shows the average number of acres burned per month, and you can see a very dramatic peak in the average acres burned in the latter part of the spring fire season, in that April, May, June time frame. This is, the transition from the dry season to the wet season. So this is also when we start to pick up a lot of our lightning fires. And the lightning fires are occurring with rain, but they're occurring at a time when we haven't got good coverage of rain yet. So fires tend to have the potential to get large during this time period as we transition into the wet period. Now, getting a little more specific to 1998, the January through March period in Florida was extremely wet. There was a lot of flooding issues. They were having to bring in hay for cattle and stuff because they had problems with flooding in some of the pastures, and to have that followed right away in the April-June time frame by one of the driest such periods on record. So they went from having flooding problems to having practically no rain for a period of 3 to 3.5 months. The city of Melbourne either tied or broke the daily high temperature record on 22 out of 30 days in June during 1998. As you can imagine, that kind of dry period led to a lot of headlines, such as this one, talking about, the unprecedented fires in Florida, and just kind of a recap of what these fires were doing. There were roughly 2,200 fires during the May through July time frame. Area burn is, rounded off to approximately 500,000 acres, over 10,000 firefighters deployed, 120,000 people approximately evacuated. Economic losses from this fire are totaled somewhere in the neighborhood of $300 million. That's not including the cost of suppression. So, overall, a very, very severe fire season, which I guess is why I was asked to talk about it. If it wasn't a fire season of note, there'd be very little to talk about. So the question comes is, was there something that led to these conditions? What brought about this extreme transition from very wet to very dry that, kind of set the table for these fires? And to get to the heart of that is really going to talk about ENSO, or the El Nino Southern Oscillation. So this area here along the equatorial Pacific Ocean is kind of where we're talking about. And basically, the El Nino Southern Oscillation is a shift in temperature patterns along within this region that ends up driving a lot of variability in the atmospheric circulation. Get this. So we're going to give a very, very simplified description of kind of what ENSO is and how it happens in a very rudimentary sense. This is going to be first, we're going to look at what's considered normal conditions. To just get you oriented here, here's the United States with Florida right over here, and then Central and South America, Australia over here. So under normal conditions, what we have is we have winds blowing from east to west across the Pacific. This is basically the trade wind circulation. And that circulation helps drive upwelling here along the coast of South and Central America, which is bringing up colder water from below. That water gets transported across the Pacific and warms up as it gets transported. Now, the area where you get a warm pool developed is going to be the area where you're going to have tropical convection triggered, indicated here by these clouds, which is going to take heat and moisture from the surface here and transport it vertically, which then begins setting up what's called a Walker cell circulation. So it kind of ends up developing a circulation that feeds itself. So if these winds change a little bit, or in the case of an El Nino event, if they weaken, we no longer have the winds driving the offshore flow, so we get a reduction in upwelling along the coast here. So we're no longer supplying the coast with a feed of cold water from below, and so you get an anomalous warming. And this warm pool begins to move back eastward across the Pacific, generally to be located more in the central to sometimes slightly eastern tropical Pacific. So we've now moved where this convection is happening, where this transport of heat and moisture is occurring into the atmosphere. Now, the opposite of El Nino is the La Nina conditions. And this occurs when the winds are stronger than normal. So that warm pool gets pushed further to the west. Again, changing the location where we're inputting energy, significant amounts of energy into the atmosphere. We have a much stronger cold pool over here due to the stronger winds at the coast, driving more upwelling. So we're bringing up more cold water from below, keeping sea surface temperatures below normal in this region. So essentially, La Nina is when we have below normal sea surface temperatures in this region of the equatorial Pacific, and El Nino is when it's warmer than normal. Now, what these circulations do to the atmosphere is we're changing where energy gets put into the atmosphere. So in an El Nino, this ends up changing our jet stream patterns, and hence our storm tracks. So quite often during El Nino, we're going to have a slightly more southerly location of the Pacific jet stream that is going to bring more storms across the southern California area, increasing their rainfall. Those storms are going to come across and bring increasing rainfall to the southeastern United States, particularly along the southern coastal plain, including Florida. When we have La Nina, we get more variability. We get the Pacific jet stream displaced a little bit more to the north. Instead of coming into southern California, it's coming into the Pacific Northwest, and we tend to get a lot more of the storms staying up along the Canadian border, dipping down into the Ohio Valley states, and then lifting out to the northeast, with fewer of these rainfall events making their way down to Florida. So in the most general sense, El Niños equal increased rainfall for the southeast. La Niñas lead to decreased rainfall and drier conditions. Now, in a couple of graphs coming up, I'm going to talk about a specific region of the equatorial Pacific that's referred to as Nino 3. This map here shows where some of the buoys are located. There's an array of buoys called the Tau Array that are located across the Pacific Ocean that are used for monitoring ENSO. So the Nino 3 is kind of this region right here in the eastern equatorial Pacific. So what we're wanting to see by looking at this region is when that warm pool shifts from west to east into this region. And we'd see that as an increase in sea surface temperatures. Likewise, when there's a La Nina, we would see more cold water moving from the coastal region here into this area. So Jim Brenner with the Florida Forest Service back in 1991 was one of the first to see that there was some degree of relationship between what was happening with the sea surface temperatures in Nino 3 versus area burned in Florida. His initial study involved, just a very short time frame, particularly for any kind of climate study, but he found a significant correlation between when the sea surface temperatures were below normal, La Nina conditions, and when you saw a peak in the area burned. Here's, there were major fire seasons in 89, 85, and 81. So the model seemed to fit pretty well, and as data was added, it still seemed to work fairly well. They had, in the early 90s, a number of periods with warmer than normal sea surface temperatures, and very little fire activity for an extended period. In 97, in early part of 98, we had the beginning of a major El Nino event. This would correspond with the flooding that occurred in January and March of 1998. But then when we reach about April, we get a rapid drop-off in the sea surface temperatures, and they actually transition to negative very quickly. Also, right about the time that things dried out in Florida and we transitioned into our severe fire season with the record drought. Now, you can kind of see some areas here where we had some low sea surface temperatures. These would probably be termed more neutral than true La Nina, because the anomalies were negative, but they weren't strongly negative. But then again, neither was the initial transition in 1998. In 2009, myself and Deborah Hanley revisited Jim Brenner's work and tried to look at it as being more than just the El Nino Southern Oscillation, where there's some other patterns of atmospheric variability that could help explain some of what was going on. And one of the patterns that we found to have an influence is referred to as the Pacific North American pattern. This is what's referred to as an atmospheric teleconnection. And really, it's just a mode of variability that shows up in the atmosphere when you do a particular type of analysis called an empirical orthogonal function analysis. And what it basically amounts to is when this index is in its positive phase, you get a pressure dipole between the North Pacific and the Southeast. In this case, it's negative pressure or lower pressures. In the case of a negative Pacific North American pattern, this would be leading to an enhanced ridging across this part of the Southeast. Now, an enhanced ridging would tend to go with those La Nina conditions. In fact, during a La Nina, you tend to get more of these negative Pacific North American patterns. So when you just look at El Nino, you can see that Florida has very little variability in area burned. So this is a measure of standardized acres burned. That's just taking the amount, subtracting the average out, and then normalizing by the standard deviation. So it just gives us a round number instead of trying to look at actual acreage numbers, which make the graph here a little bit harder to look at. But it's easy to see that pretty much all El Nino years end up being below normal, which in this case would be 0, with very little variability. You contrast that with all years that occur as La Ninas, and you see, one, the mean is much higher. The variability goes from having minor fire seasons up to the most extreme that have been recorded. And generally, the plus or minus 1 standard deviation from the mean is, again, very large amount of fire variability, and neutral ENSO events when it's really not really warm or cold, so say sea surface temperature anomalies between minus 0.5 degrees and plus 0.5 degrees, you have kind of what would be considered average fire seasons. In fact, the average here is almost just below the 0 line here. But when we look at the addition of information from the Pacific North American pattern, we see that still all El Niños fire activity is extremely low. But during a La Nina event, there's a big difference between whether this Pacific North American pattern is in its positive phase or if it's in its negative phase, which enhances ridging across the southeast. So enhances the pattern that would lead to dry conditions. In fact, almost all of the bad fire years that are contained within this bar graph occur during La Nina with the negative phase of the Pacific North American pattern. So let's look a little bit more closely at sea surface temperatures in the equatorial Pacific. So this graph has longitude across the Pacific Ocean versus time. So we start up here with January of 1997, and you see the strong El Nino event proceeding till right around April of 1998, and then it abruptly transitions to below normal sea surface temperatures. So we almost go as a switch from El Nino to La Nina conditions right at the time that Florida transitioned from extremely wet and flooding to record dryness. Now, while this abrupt transition is a little troubling, further investigation revealed that it would have been possible to see this event coming if instead of looking at just the sea surface temperatures, we looked at the depth averaged sea surface temperatures. So looking at the depth average, again, we're starting in January of 97, moving through our El Nino event, and then as we get to the March, April, May of 1998 time frame, we see this pool of cold water basically moving across the Pacific Ocean from west to east. This is the change in the slope of that thermocline, indicating that we're starting to build up some more upwelling along the coast of the Pacific. So we're seeing that transition happening at a deeper part of the ocean. So the event could have been seen that the transition was going to happen. Now, here on this graph, we're looking at the Pacific North American pattern. And right at the time that the transition happened, we quickly switch to that negative phase of the Pacific North American pattern, which is the preferred phase during a La Nina event and tends to lock us in to that enhanced Bermuda high, that strong ridging across the state. So now if we go and look at what's going on right now to see how things stack up between our 2016 year and 1998. Here are our sea surface temperature anomalies, and we see the strong El Nino event that started in 2015 and has persisted to current conditions. And if we look at the depth average temperatures, we see that there is cold water, but it's still largely being held in the western Pacific Ocean. And compare that to 1997, where we see that it made significant progress back across the Pacific. Let's put both graphs up at the same time. So we have 1997 here on the right, and 2016 on the left. And the cold water is still generally west of 170 west longitude, where in 98 it had already moved all the way, to around 140 west longitude. And another thing to look at is the El Nino event is kind of oscillating, but it kind of peaked here in the November-December period in 1997 and then began to decay as you went into 1998. In 2016, we see similar oscillations. We're not quite seeing that decay. In fact, here recently in January and February, we saw another peak. So the El Nino doesn't appear to be decaying quite as quickly as what happened in 1998. We can see that with the strong El Nino, the Pacific North American pattern has remained pretty much locked into that stronger positive phase, promoting less ridging across the southeast, creating an environment conducive to the development of storms moving across the area. Now, the projections for what's going to happen with the sea surface temperatures in the equatorial Pacific. So this is an ensemble of projections of from where we currently are. At the time this forecast was done, it was started in December of 2015, and how the sea surface temperatures are going to evolve. You can kind of see that by the April, May, June time period, there's still pretty good consensus that we're going to be in a warm event, unlike the rapid transition that occurred in 1998. Now, of course, these are models. They could be absolutely wrong. But normally when you look at an ensemble of models and they're all giving you pretty much the same answer, it gives you some confidence that that transition to La Nina is not likely to happen until we get into the summer. So there is strong evidence that the El Nino Southern Oscillation and Florida wildfires are closely linked. And in fact, that linkage extends not just to Florida, but much of the southern coastal plain. The 1998 Florida wildfires occurred at the end of a strong El Nino with a rapid transition to a La Nina event. And that transition, the timing of it, happened to coincide with the time when the peak conditions are generally ripest for burning the most acreage. So 1998 could be expressed as bad timing all around. (2016) does have some parallels to 1998. We have a strong El Nino event occurring. The event is expected to decline and end generally in the summertime frame, but a couple of those models had it ending late spring. One key difference between the two time periods is shown in the depth averaged temperatures. For 1998, we saw that cold water generally just linearly progressing across the Pacific Ocean, while currently it's still predominantly in the western part of the Pacific. So we're not seeing quite the same signal. And that difference gives me some confidence that we're not going to get the same exact timing, that we're not going to get that rapid transition to conditions that are going to favor the development of record-setting drought in heat. It's not to say it's not going to happen, but indicators don't line up as an exact match to what happened in 1998. For those looking for some additional resources, Much of the information that was displayed here came from these sources. There's a link in here to the Pacific Marine Environmental Laboratory from NOAA that houses the tau array buoy data and provides utilities to create those depth average plots so that they're actually fairly easy to go look at. And with that, we're right about 30 minutes, so I think it's time to go ahead and open it up for questions.
So it looks like we have some folks type in. Scott, I'm going to ask a couple of my own questions just to kick things off. One, if you could kind of explain a term that I'm not familiar with, which was enhanced ridging. And then the second question after that is it seems like it's important to understand the impacts of La Nina based on that the P&A values as to whether or not P&A is in the positive form or the negative form. Is that something that that managers could find online to understand what form P&A we're in as we move into the La Nina this spring or this summer, depending on timing?
All right, taking your last question, yes. There are places to look it up on this ENSO info resource list. The last link on there is to the NOAA's Climate Prediction Center, and it has pretty much everything you need to know about the Pacific North American pattern. You can get current status of the index as calculated by the Climate Prediction Center, as well as forecasts of it that generally go out. I believe they have forecasts out as far as about 14 days to possibly 30. Now, the enhanced ridging, ridges of high pressure are what generally bring us dry, bad fire condition days, particularly when we have the Bermuda High that can extend across the southeastern United States. So when I spoke of enhanced ridging, it was a strengthening of that high pressure ridge. So a stronger high pressure would lead to drier conditions, more suppression of rainfall, generally bad fire weather pattern.
Well, thank you. All right, it looks like we have some questions that have come in, and we'll just kind of take them in order there. You can see, it looks like the first one came in from Cabe, and it says it appeared that there were several periods of La Nina over the years, but with low fire occurrence. Can you explain that? Yes,
some of those periods of La Nina or below normal sea surface temperatures, that kind of sometimes that gets into the gray area where it's below normal, but it's not enough below normal. That kind of gets into what we refer to normally as a neutral ENSO event. So generally, when those sea surface temperature anomalies are between plus or minus a half a degree, they're not different enough from zero to make much of an impact. A few of those other cases, some of this is that we're talking about correlations, and correlations don't necessarily imply causations. There's a whole bunch of other things that have to come together to get the bad fire conditions. If we get the La Nina conditions at a time when we've got some other competing atmospheric variability, we might get, like say, the North Atlantic Oscillation is another oscillation that's been found to play a role in kind of guiding the large-scale dynamics. It didn't turn up in my study to have a strong impact, but it might have enough that it could blur that correlation somewhat.
We have another question that came in from Marco, and he asked us, did early flooding yield the flush of vegetative growth similar to western fires, the fuel? So did that lead to excessive fuels when the ensuing drought occurred?
I'm sure there was probably some of that. And if you think back to that graph of the area burned from 1991 to 1998, they hadn't had any major fire seasons preceding that. And many of those were weak El Nino events, so favoring rainfall. So it could have been multiple years worth of enhanced growth and accumulation of understory vegetation. With the southeast rapid vegetative growth, absolutely, rainfall in the January through March period would lead to increased growth, which could result in increased fuel loads come that April through June dry period.
So then Jonathan had a question going back to the P&A. Jonathan McCall says, how is the P&A predicted to correlate with the La Nina of 2016?
Well, I'd say the P&A generally tends to go negative when, there's the P&A varies much more than El Nino does. So the P&A can change on this time frame of days to weeks, where ENSO changes much more slowly since it's the warming and cooling of the ocean. So what generally happens during a La Nina is you will see more periods of the negative phase of the Pacific North American pattern. There's kind of a preference for that pattern to emerge over the positive phase. But you will still get a mixture of the two.
So then we had another question that looks like from Brian Williams. Does the Hadley circulation have any play in the east-west circulation that you showed earlier when you were talking about ENSO?
Yes, and that starts to get in some of the complications I was trying to keep out of, having to deal with the more three-dimensional nature of the pattern. But one aspect of the Hadley cell, so the Hadley cell is kind of a north-south version of that east-west circulation I was showing. And one thing that happens in the Hadley cell is you have that convection lifting energy up, and part of the Hadley cell's job is to transport that energy and moisture northward. Now, when we have an El Nino and that warm pool is located in more of the central to east central Pacific, you can see that a lot of that moisture, as it comes up and gets transported to the north, it's actually going to head towards the southeastern United States. So we'll tend to get a warming of upper levels of the, more of a moistening of upper levels of the atmosphere during an El Nino, which would make any convection that starts over Florida more likely to continue and generate rainfall. Because it's moving into a more humid environment, you won't get as much evaporation. Whereas if you have La Nina, where now that most of that convection is off in the far western Pacific, that energy and moisture transport isn't coming up over Florida as much.
So then we had a question from Alan. There have been some projections that the projected ENSO changes this year, along with some other oscillations, point to a strong hurricane season in the southeast. Could you comment on that?
Well, traditionally, La Nina is the one that brings an increased probability of hurricanes. So there would be a possibility, if this transition occurs in the June-July period, it would happen early enough to favor the potential for an enhanced hurricane season. Generally, most bad weather that you can think of comes with La Nina. We tend to get more hurricanes during La Nina. We tend to get more tornadoes during La Nina. So kind of go hand in hand.
So La Nina is really the one to look out for. Adam asked a question. He says, this is really looking farther out. He says, what do you think we can expect as far as Florida and Georgia fire seasons over the next 1 to 4 years?
Well, if it does indeed follow a pattern similar to 1998, we went from a very strong El Nino into a moderate to strong La Nina that persisted for a number of years. 1998 was just the first of several bad fire seasons, particularly in Florida, in Georgia. So while the initial 1998 part can be racked up, to timing of the transition to the drier conditions right as we're getting to when the peak acreage time is, we might miss that this year. But we might see the transition to a prolonged La Nina. Currently, most of the expectations are for neutral conditions to persist. But to be honest, neutral normally doesn't last that long. It normally goes one way or the other.
Mm-hmm.
So I think there might be potential for another prolonged period of above average wildfire seasons that might come. We might not catch it this year, but it might come next year.
Mm-hmm. So then, Aaron then asked if the La Nina event occurs later this year than it did in '98, would that suppress or eliminate the Florida summer rainy season? I think you sort of covered that just now.
Yeah, well, the Florida rainy season has never been eliminated.
Mm-hmm.
It's driven by very local phenomena. It's driven by the relationship between, being a big peninsula stuck out there in a big body of water. So nothing has ever completely stopped the development of that rainy season. It's been delayed, and 1998 was probably the biggest delay to its onset that we had seen. But even it was not enough to stop it from developing. So no, I don't think it would be able to stop it from occurring.
And then we have, looks like our last one here is from Young Lee. Storm track stays in the south during El Nino. How do you explain the severe drought in California last year when we have a strong El Nino?
Thanks, Young. I love that question. There's obviously more that goes on than just El Nino, La Nina. I haven't looked very closely at the exact role, but my guess would be that there were other atmospheric teleconnection patterns at work. Something, kind of shifting the pattern a little bit from what we were expecting. For California, you shift that storm track north or south a little bit, and some areas get rain while others get nothing. So I'm really not sure, but I think that close examination would show that there's some other modes of variability in the atmosphere that would have influenced that.
And then one more from John Cookian here. It says, are the models predicting the monthly sea surface temperature, or are they the 3-month average? And if it's the 3-month average, then wouldn't they be under-predicting the possible rapid temperature drop?
Well, the graphs that I was showing was predicting the 3-month average. There are graphs that are predicting it by month. I showed the ones doing 3-month more for clarity of presentation than for content. But that being said, the plots were consistent. I didn't see anything that really looked that different looking at the actual monthly data compared to the 3-month average. Some of that's just due to the nature of the models. But the choice for presenting the 3-month was more for presentation clarity. It doesn't change what I was seeing as far as the where the cold pool was currently located on the depth average temperatures and how rapidly that would likely move across. So yeah, it really does. Whether the predictions are monthly or 3-month really didn't change anything.
Mm-hmm. Looks like that's. I'm going to go ahead and throw out the last question here, and then we'll get things wrapped up. So, we've been talking a lot about Florida and Florida's fire season. That's kind of our key here. But how much of this, Scott, is really going to apply to other folks, you think, in the southeastern Gulf Coastal Plain, our folks in Mississippi, Alabama, or the Carolinas?
Well, there was a study done back in 2007 that showed that much of the southern coastal plain, I believe the study was by Dixon, Goodrick, and Cook, that looked at some of these different teleconnection patterns and wildfires, specifically in Mississippi. And they found very similar relationships. Their relationship wasn't quite as strong with the Pacific North American pattern, and some of that could just be being located, further west, so you're not quite as close to where that Bermuda high is being enhanced by the Pacific North American pattern. So there could just be a little bit of difference in that. But generally, the ENSO signal holds throughout most of the coastal plain pretty well.
Okay. All right. Well, thank you. And so we're going to make sure that our folks from the Carolinas all the way over to Louisiana, Mississippi, Alabama, maybe even Texas should be paying attention to this as well. Well, Scott, it looks like we've run up to about the end of our time for today, and I'd like to thank you very much for your presentation and for joining us.